stop picking ANN indexes by vibes. We'll generate ground truth, measure recall at K, then compare P50 P95 latency. So the winner is obvious. By the end, you will know how to measure search quality and latency, so you can pick the right ANN index with evidence, not guesswork. I'm Professor Pi, teaching search and IR with simple Python. ANN choices show up when exact nearest neighbor search is too slow for your data or traffic. The practical problem is simple. You want similar items fast. You also want to know how much quality you trade for speed. Success means you can point to numbers that justify an index choice. For engineers, that means recall and latency numbers you can reproduce. At a high level, the harness does three things. First, it creates a reliable ground truth using an exact search. Second, it defines an objective metric that captures how many correct answers survive in the top results. Third, it times competing ANN methods and compares both recall and tail latency. The goal is a single table you can use to choose an index. We will build a compact experiment that uses the same toy corpus across every step, so comparisons stay honest. You will see flat exact search for ground truth, an IVF variant in FAISS, a graph index in HNSWlib, and a simple timing run that prints median and tail latencies before we decide. Now, let us start with the exact reference search. This snippet builds a FAISS Flat L2 index and computes top 1 ground truth. It creates a flat brute force index in FAISS and adds the corpus vectors. Then it runs a search for each query and records the single best neighbor as the canonical answer. The core idea is to use FAISS Flat as a deterministic baseline. So every approximate method is measured against the same correct labels. Key lines add vectors to the index, call FAISS search for top 1 results, and collect those targets as the ground truth set. This step is the anchor for all later recall calculations. Next, we implement a scorer that measures whether an ANN returns the ground truth in its top results. This example defines recall at K and validates it against FAISS Flat search. The code shows a function that accepts returned neighbor lists and the ground truth mapping, and computes the fraction of queries that include the true neighbor within the top K. It then runs this function against FAISS Flat results to check that recall at K is effectively 1 for top 1 on the baseline, or to validate implementation details. The snippet highlights how to structure results as simple integer lists per query, and how to compute recall as hits divided by total queries. Changing K widens the window and usually increases recall. Now we build an index that trades off accuracy for speed with clustering-based pruning. This code builds a FAISS IVF flat index and measures recall at K. It trains an inverted file index in FAISS with a chosen number of coarse clusters and then adds the corpus vectors. At search time, the code sets the number of probes to control how many clusters get scanned. The snippet measures recall at K by running the same queries and comparing returned neighbors to the ground truth from the flat index. Practically, increasing the number of probes improves recall, but also increases query time. The paragraph explains where to tune for your accuracy versus latency constraint. Next, we add a graph-based index to the same experiment and compare its behavior. This snippet creates an HNSWlib index and computes its recall at K. It builds a small world graph-based index with HNSWlib using the same corpus vectors, sets construction and query trade-off parameters, and runs queries to get neighbor lists. The snippet then applies the same recall at K function, so the metric is comparable to FAISS results. Parameters like graph connectivity and the search effort parameter change both quality and speed. Higher search effort typically increases recall and also increases latency. The important point is the harness treats both libraries the same way, so comparison is apples to apples. Finally, we collect timings and compare tail latency between the fast candidates. This example times FAISS IVF and HNSWlib and reports P50 and P95 latency. The code repeatedly issues queries and records individual query times, then computes P50, the median latency, and P95, the 95th percentile latency. The snippet prints both recall at K and these latency percentiles for each index, so you can see the trade-offs. Measuring many repeated queries is important because P95 reveals stability under load, while P50 shows typical speed. The timing run uses the same query set and warmed indexes, so the numbers reflect the search step alone. Mapping this toy experiment to a real system is straightforward. Replace the toy corpus with your embeddings. Run the same harness, and the harness will show how recall and tail latency change at production scale. The relative ordering of methods tends to persist, and the tuning knobs behave the same way in larger runs. Recap: what it is: a repeatable harness that builds a flat ground truth, computes recall at K, and measures tail latency. When to use it: whenever you need objective evidence to choose an ANN index for production search. One caveat: toy numbers are directional, not final. You still need a slice test on realistic traffic and data. Next step: tune FAISS nlist and nprobe for your corpus and rerun the harness to find the cost versus recall sweet spot. If practical IR and reproducible choices help your work, subscribe and watch the other videos on search and evaluation.